So graphing in polar, I'm not going to worry about changing this to rectangular coordinates. We're just going to stick with polar. So I need a polar grid to graph this. And then I'm just going to go back to basics for graphing. What does it mean to graph? It means to plot enough points that you recognize a pattern. So we're just going to pick some numbers, theta, the independent variable, and calculate r based on this equation there. So I'm just going to go some of the standard favorites, 0, pi over 6, pi over 4, pi over 3, pi, and see if 5 points are enough to see the pattern. If not, we'll plot more. So cosine of 0 is 1. Cosine of pi over 6 is the square root of 3 over 2, which is around, I'm going to just call it 0.8. It's closer to 0.9, 0.86, maybe we'll do that. Cosine of pi over 4 is square root of 2 over 2, or 1 over the square root of 2, which is about 0.71-ish. At pi over 3, we get a half, and then at pi, we get an x value of 0. So let's graph those r theta. So given that these numbers are at most 1, I'm going to, let's see, use 1, 2, 3, 4 circles. Let's go 5 circles out here. So the 5th circle out on mine is going to be 1. So I'm scaling by 2/10, right? 0.2, 0.4, 0.6, 0.8, 1. And then otherwise going around, right here is my pi over 6. Right through the middle there is my pi over 4. Here's my pi over 3. Here's my pi over 2. Oops, pi over 2, I lied there. All right, so I'm starting off with the point 0, 1. And then at pi over 6, I get about 0.86. So here's 0.8, 0.9 is right there. So 0.86 is like right in between here. So maybe around there is that point. And then at pi over 4, so this line coming out, we're at about 0.7. So 2, 4, 6, 8.7 is right in the middle here on that angle. So around there-ish is the next point. And then 1/2, so 2, 4, 6, 1/2 is right in the middle. And I want to come around to its angle there. Interesting, these 2 points kind of line up horizontally. And then I hit, at pi over 2, I have radius is 0, so I'm stuck at the pole here. So interesting shape there. In between 0 and pi over 6 would be pi over 12. Kind of curious where that one lies. About a calculator for that. I'm going to use Geogebra today because I like the way it graphs polar stuff, because I can actually do polar points. And the other thing I like about Geogebra, it has, instead of a grid here, I can go to settings, and say change the grid to polar. And it's scaling by pi over 6 here. So you could pick a different scaling factor if you click on distance, and then you can rescale by like pi over 12 maybe, which is what I'm about to do. All right, and really at the moment, I just want to know what the cosine, actually we can graph this point in polar. Remember, points in GeoGebra for polar have a semicolon. So first I enter r. R here is the cosine of pi over 12, and that looks like it's interpreting it as radians. And then semicolon, well, that's r, let's see. Yeah, r theta, right? Semicolon, and then theta is the pi over 12. And so there's that point. Let's zoom in, zoom in. All right, so this says the radius is about 0.97-ish. Let's go to my graph. So at pi over 12, this line coming out, 0.9 is here, 0.97 is pretty close to that one circle. So I'm gonna guess that's about right here-ish. And so my points seem to be coming up and through and over and down. And that looks like a semicircle. So I'm just going to graph a couple more points and then have the computer graph it to prove that. So next regular angle, next special angle would be over here. That would be 2 pi over 3. And then here, 3 pi over 4. And then here, 5 pi over 6. And then back here at pi. So let's look at those. So 2 pi over 3, 3 pi over 4. 5 pi over 6, and pi, what's the cosine of each of those? Cosine of 2 pi over 3 is going to be a -1/2. And then 3 pi over 4 is negative square root of 2 over 2, or about -0.7-ish. 5 pi over 6 is just going to be the opposite of that up there, so about -0.86. And then at pi, it's going to be -1. And remember, a negative radius means find the angle, then go back through the pole. So for example, at 2 pi over 3, I want to think about that angle. Positive radius would be this way. Negative radius goes back through the pole this way over to -1/2. So let's see, 2, 4, 6, that would be right in here. So that point is around there. And then 3 pi over 4 is this line, but we're coming back because it's a negative number to 0.7, which is about here. And then 0.86. So here would be the angle for a positive radius. Negative radius means go back through the pole. That's going to be around here-ish. And then pi, normally positive radius would be this way. So negative radius, I go that way. So that hits there. So this graph traces in this direction. And it looks like I'm making a circle. And then what happens if I keep going? So let's check. Oh, I guess we can calculate one more point and then go to the computer. Over here, what would that be? Let's see, this is 5 pi over 6. This is 6 pi over 6. This would be 7 pi over 6. Reference angle there is pi over 6. Cosine of 7 pi over 6 is going to be negative and square root of 3 over 2. So about -0.086. So positive radius would head out this way. Negative radius heads back. So this point right here is plotted both for pi over 6 and it's plotted for 7 pi over 6. Those two are the same point. So it looks like this is a periodic function right here. And it should be periodic, right? It's a cosine in some way. But we have a totally different graphing framework here, right? This isn't the wave that we're used to in rectangular coordinates. And the period here is pi. So this seems periodic, period pi. All right, so now that we did one by hand, we can just use the calculator. And I'll show you a couple of ways to do it. I like to use GeoGebra, but Desmos has another way to do it. We'll look at Desmos too. So to do polar in GeoGebra, points have a semicolon between them, the value of r, then the value of theta. For graphs in polar, we have to use the curve function. And so I type curve and then my parentheses. And what the curve function needs is, for polar, it needs a polar point. So I'm going to put parentheses with a semicolon. It needs what is the independent variable. So I'm going to use t instead of theta. My independent variable is t. And then it needs where do we start t and where do we end t. So I'm going to go from 0 to pi. Now, as far as the polar point goes, here we're going to enter r as a function of theta. So that would be the cosine of, and I'm using t instead of theta here because it's easier to type. And then the angle is t. And so then it does the graph for me. So again, I'll write down how that works again. So there's the graph. If I go less than pi, like maybe what, 5 pi over 6. So if I make this instead 5 pi over 6, then right, I don't quite get a full cycle of this thing. And then as I add more than that, like suppose we go out to 2 pi, then all it's going to do is redraw itself, and we're not even going to see anything happening there. Right? So at 2 pi, it looks no different than pi. But if I go any less than pi, oops, so like 3, I don't quite get, notice if I stop at 3, pi is just a little bit farther, I don't quite get the full circle. So I'm just trying to confirm that this is periodic, period pi. All right, so quick note on graphing in GeoGebra. So Geogebra Polar. First, I like to go to the settings and then change in the second part of the settings again. I like to change the grid to polar. To do a point, it's whatever R is semicolon and then whatever the angle is. To do a function, like R equals f of theta, I'm going to use a t instead. So we're going to call it R equals f of t, because it's easier to get a t in GeoGebra than a theta. I got to dig into the menus to get the theta. I would use the curve function. So curve, parentheses, and then I give it a polar point where I type whatever f of t is, semicolon t, and then I confirm the independent variable is t, and then I tell it where to start and then where to finish. And I went to 2 pi in one example. So again, important things here. This is the end angle. This is the start angle. Here I'm confirming the independent variable. And then this part here, the first thing has to be a polar point. With your function and then your independent variable. And that'll make any polar graph you want. In Desmos, we'll go back to the course homepage and get the polar coordinates in Desmos and GeoGebra and Desmos. And so here I have an example of something like what I just did there. And then down here is a link to the Desmos graph a friend of mine set up. So to make Desmos look like polar, he had to plot a whole bunch of circles. So that's what these are here. And then a whole bunch of lines. And then at the top here, we can put in whatever function we want and we can set boundaries. Otherwise, GeoGebra will guess. So right now there's no boundaries set because they're grayed out, but I could always type something in. So we just graphed cosine of theta, which is just a circle of diameter 1 there. We could prove it's a circle of diameter 1 by changing it to rectangular coordinates to see that it looks like a circle equation with the whole x squared plus y squared thing. But I think it's just way more fun to just graph in polar. And if we multiply by the cosine by something like, say I do 2 times the cosine, that just changes the diameter from 1 to 2. If I multiply by 3, I now have a circle of diameter 3. So that's kind of a cool observation we can add to our notes here. So based on the graph we just made and playing around in GeoGebra, we just looked at things that look like R equals, I'm going to call it some number D times the cosine of theta, gives us a circle with diameter equal to D, and then the center of that circle in rectangular coordinates would be the point x is whatever d over 2 is, half the diameter, right? So 1/2 is right in the middle here. That was radius 1/2 there. And then the y value is 0. And if we were to, like we were playing around last time with converting polar to rectangular, if we were to try and convert this to rectangular coordinates, we would see, oh, the equation for that thing would look like x minus 1/2 squared plus y squared equals 1/2 squared, right? Because if the diameter is 1 here, then the radius would be 1/2. So again, if you did try to convert this like we were converting before, you would end up with that right there. All right, so let's play a little more. So some other polar functions I wanted to play with. What if instead of putting like a 2 on the outside, what if we put it on the inside? What happens? So we'll try this in both GeoGebra and Desmos. So, and again, this should really have a parentheses. When I lost my theta, I gotta get that back. I think my recollection is in Desmos, I just type theta and it rewrites it. There we go. All right, so there's the one we started with. If I put a 2 on the outside, that increases the diameter. What happens if I put the 2 on the inside? So in rectangular coordinates, that gave me this horizontal compression. What happens in polar coordinates? Whoa, what the heck is that thing there? Let's zoom in on it. It's like a 4-leaf clover. All right, I'm gonna graph that in Desmos, or no, that is Desmos. Let's go to GeoGebra to graph it too. So once I type the curve thing once, I can reuse it. So I don't need this point anymore. Let's get rid of that. And so all I'm gonna do here is I'm gonna sneak in and put a 2 times the cosine there to tweak this function, hit enter. All right, now here I only went up to 3 and you can see I didn't quite finish this. So this period here is bigger than pi. When we just did the cosine of t, the period was pi. Once I throw a 2 in there, the period is no longer pi. What is the period? Well, we can play around and check. Let's expand this a little bit. So I went out to 3, which is a little less than pi. What if I went out to 2 pi? Enter. Ah, okay, looks like 2 pi completes the whole thing. Now, if I'm not quite sure of that, I'll just go a little less than 2 pi. So pi is 3.14, 2 pi is 6.28. So what if I only went up to 6 here? Then I can see, oh yeah, not quite. What if we did 6.2? Yeah, a little closer. I need that 0.8 blah, blah, blah. So it looks like the period here is 2 pi. So the polar world is a very different universe than the rectangular world, but it turns out it's an important one. There's lots of things in the real world and mathematics that relate to this. So I get a 4-leaf clover here. When I do 2 pi, check out 2t, check out 3t. This is cute. Oops, 23t. No. 3t, please. There we go. So with 3, I get 3 leaves. That's interesting. With 2, I got 4 leaves. Oh, interesting. Let's make a note of this. What's going on here? This is wild. So let's see. R equals cosine of 2t or 2 theta gave me 4 leaves. All right, so let's see, and how are those leaves oriented again? Okay, like that. So it went something like this. And this is actually, ooh, is that the way it's graphed? No. Cancel. Undo. Okay, so I think it starts at the pole, and my recollection is it goes out, around, up, around, out, around, down, around. And it doesn't have an overlap there. That's just me being sloppy. So I think it graphs this leaf first, this leaf second, that leaf third, that leaf fourth. I believe I have a way to demonstrate that in a minute. when we did r equals cosine of 3 theta, and now here I went 2 theta, 4 leaves, 3 theta was 3 leaves. Interesting. All right, let's play. So I think if we go back here, I want to leave. The other graphing tool I had for GeoGebra will actually trace it slowly for me. So let's check that out. Yeah, when I set this one up, I designed it so that the angle here traces it out, starting with a equals 0 for the angle, which is the same as t here. I can't remember, I had a reason I had to rename those t and a. Okay, so let's put that back to 0. And then over here, we're gonna graph. First, we'll do the cosine of 2t to see what it looks like. And I don't think I need to hit enter. And then I start tracing. Oh, it goes down first. Okay, so I had the order wrong. And then it goes out to the right, and then it goes up, and then it finishes the leaf, right? Because cosine starts at 1. All right, so I had that order very wrong. See how that goes? So if we plotted points, we would have seen the way that this is traced. And then we can see once we get to about 6.3, we've gone a little past completing all 4 leaves. Let's take that back. Let's see what 3t looks like. All right, and then put a back to 0 here. Scroll up. And the scroll on here, you got to scroll on the side here. If you try to scroll in here, it'll zoom in and out. All right, take a to 0. So here is the 3-leaf one. So we head out and then down for that lower leaf, and we head up, and then we head back, and we're back at about 3.1. So that would be, around pi should complete it. Notice I haven't quite completed there if I were to zoom in on that point. All right, so let's fix my notes. My order of operations was incorrect here. Let's see, erase. Ooh, that's a big eraser. So this one here started there and went around. So that was the start. And then it went down. So this was the start here. And then it jumped over to this leaf. So this is like the second part. And then it came around, and this was the third part here, this leaf in that direction. And then this was the fourth leaf. And then it came back here to finish. Cool. All right, so 4 leaves with a 2, 3 leaves with a 3. Let's see, what if I put a 4 here instead of a 2? I think that'll give me 8 leaves. And what about a 5 here? Will that leave 5 leaves or 10 leaves? Let's take a look. So all I have to do is go in here, any one of those apps, and just replace that 3 with a 4. And I have, I haven't graphed enough here. So I got to graph some more. And there are 1, 2, 3, 4, 5, 6, 7, 8 leaves. Okay. And then if we put a 5 there, we get 5 leaves. Cool. All right. So there's a pattern going on here. So if we graph r equals cosine of 4 theta, we get 8 leaves. If we were to graph, which we did, r equals, different color, please. Cosine of 5 theta, we get 5 leaves. So it looks like if we consider in general, r equals cosine of, say, b times theta here. If b is odd, then we get b leaves. But if b is even, then we get 2 times b leaves. Now, there's no reason b has to be a whole number. We can multiply anything we want, like a half or 2/3. So what if I go in here, instead of a 5, I do 2t divided by 3. Ooh, what is this? Need some more. So apparently 2 pi wasn't enough to complete a cycle. Whoa, that is wicked cool. So then we get these funky overlapping leaves. So what I see here is 4 big overlapping leaves here. I see these big butt-shaped curves here. So I get 4 butt flowers that overlap. What if I switch the 3 and the 2? Oh, so then they're not butts, they're just these balloon type leaves instead of butts. Nice. So the polar world is very, very different. It's a totally different universe than the rectangular world, but there are some important things here. All right, so we're going to move away from polar graphs. You will see this stuff again if you go on to like calculus 3, if you go into any electrical engineering stuff and mechanical engineering stuff. These things become important to do calculations. Anything that's circular is easier to do in polar than rectangular. All right, new topic. I can find Zoom. Zoom, where'd you go? There you are.